Welcome everyone. In this video we are going to practice solving trigonometric equations. The equation that we want to solve is this. 5 sine squared theta, I mean x. Yeah, we don't use theta even though it is common to use it for angles. 5 sine squared x plus cosine of x equaling 2, let's say. And I want the solutions for the case where x is between 0 and 2 pi radians. Okay, because otherwise, since cosine and sine are cyclic, you would have infinitely many solutions. Perhaps you would have infinitely many. Maybe there are none. Who knows? Anyways, why don't you pause the video, give this question a trial, and when you're ready, continue the video, please. Alright, I assume that you tried it yourself or you just want to see the solution. In either case, let's do the problem together. So the first thing that I want to do here is I want to get rid of the sine squared. Because, if it is like this, I can't factor it. There is no way that I could factor it. I want to turn this to a second degree equation, to a quadratic equation, but the variable won't be x, it will be cosine of x. And that is just okay, it doesn't really make much of a difference for the solution. So I will use the Pythagorean trig identity, that is, and let's write that with orange. Sine squared x plus cosine squared x equals 1. And you might be saying, oh, I don't trust you, I don't think that this equation is correct. Well, if that's what you're saying, you're on the right path. You don't need to trust me. I have a video about this where I prove that this is in fact correct, and you can access that video from the cards right now and also from the descriptions part. Remember, in math and physics and in science general, don't take anything for granted. Always look for the reasons behind them. And there is a reason, like a 10-minute video, where you can see that this is in fact correct. Cool? So, with that being said, what is sine squared x then? It is sine squared x equals 1 minus cosine squared x. And now we're just going to substitute this here. And let me just distribute the 5 as well. So we have 5 minus 5 cosine squared x plus cosine of x equaling 2. Let's toss all of these to the right side. So we have 5 cosine squared x minus cosine x, and then a minus 3, equaling 0. Cool. Now at this point, we might try factoring this out, but in fact we won't be able to factor it out with integers, okay? You can try it. I already did this problem before the video, obviously, to make sure that I am presenting something right to you guys. So I know that you can factor this. And let's give it a go, why not? Maybe you have 5 here, 1 here. Negative 3 here, 1 here. That doesn't work. Maybe 1, 3, negative. No, it doesn't work, okay? So let's use the quadratic formula. And when you use the quadratic formula, if this is factorable, then the square root will give an integer. Okay, so you will understand, you will say, oh, I didn't see that it was factorable, but there is no problem. The quadratic formula works for any type of second degree polynomial, whether they are factorable or not. So let's use the quadratic formula. We're going to say then that cosine of x equals, and let me write the general formula as well. So this is the general formula. Hold on a second. Let's change the color as well. Let's do it with green. This is the general case for a second degree equation, second degree polynomial, a quadratic equation, let's say. And the solution for this is, there are two solutions at most, two real solutions, or there can be imaginary conjugates as well, or there can be a double root. The solution is negative b plus or minus b squared minus 4ac over 2a. And this is another formula that you should not trust, because I have a derivation of this. You can access that as well from the cards and also from the descriptions part. And please, 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 do watch the derivations of these two. I would argue that they are more important than the question itself. Okay? Derivations and proofs are very important, and that's where the name of the channel, Proved, comes as well. Okay? So, well, let's just use this for our case then. Negative b is the coefficient of cosine of x, which is negative 1. Then we have the negative, so it is 1. Plus or minus b squared is going to be 1 minus 4 times a, which is 5, times c, which is negative 3. And then we divide that by 2a, which is 10. So cosine of x is 1 plus or minus, well, let's see, it's going to be 20 times 3, 60, 61 divided by 10. And as you can realize, the polynomial was in fact not factorable because we have a, well, we have the square root of 61 basically. We wouldn't be able to come up with this factor if we did not use the quadratic formula. Are we done? No, we're not done. Because we want to find x. But we really took a huge step towards finding x. Because, I mean, at this point, maybe you would say, alright, I got this. I'm just going to take the arc cosine, the inverse cosine of this, and there is my answer. That will be one of the answers. But there are others in this interval. And the way that you can understand that there are other answers is by considering a unit circle. Okay? We have this x and y, and the unit circle is like this. It has a radius of 1. That's why it's called a unit circle. And let's say that we are considering the positive sign here, and we find x1, and let's write these with this color. So x1 is going to be arc cosine of 1 plus the square root of 61 divided by 10. Okay? That would be, let's say that gives an angle, and I mean, I know that it's going to give some angle that is, well, this is positive, right? So basically, I mean, you can sense that it is going to give something in this region. That's where the positive cosines lie. Because the cosine is associated with the x-coordinate, right? And if you know something about the domain of the arc cosine function, the inverse cosine, you know that it only gives values in this interval, okay? From 0 to pi. So in fact, I mean, if we look at the intersection, the cosine is positive, so we should get something like this, something that is in there. And since the domain of arc cosine is like this, the intersection is the first quadrant. So this is going to give an angle that is in the first quadrant. Maybe it is like this, okay? Who knows? x1. And in fact, I already calculated what x1 is using a calculator. It is going to be approximately, of course, 0.493 radians, okay? So it is in fact in the first quadrant because it is less than pi over 2. And it is greater than 0. And the other solution would be, these are the two obvious solutions, I think. x2 would be, if we consider the negative this time, arc cosine of 1 minus the square root of 61 divided by 10. This is going to be, and I will write the approximate result, but let's first argue for it. So if we look at the numerator, we know that it is going to be negative. So it should be here, somewhere here. And since we already discussed that the domain of the arc cosine is here, we know that we are going to get a result that is in the second quadrant. So maybe, well, maybe x2 is, I don't know, like this maybe, who knows. Like this. That's x2. And if you were to type this to a calculator, you would see that you get the result 2.32. Okay? And this is in the second quadrant. It is greater than pi over 2 and it is less than pi. Now comes the other two solutions for our interval. And you can sense where they are going to come from. Because look at this. if we were to reflect this x1 with respect to the x-axis, there is going to be another solution. And let's color code these with pink, with purple. This is kind of purple or pink in the middle. There is going to be another one, and it is going to be all the way like this, which I will call x3, let's say. Or, you know what, let's call it x4, because it's going to be the greatest of the four. And how do I know this? Well, because basically, even by looking at the picture, you can see that this is a symmetrical case. So if we were to, we rotated x1 radians in the counterclockwise direction. If we rotate x1 radians in the clockwise direction, we still get the same cosine value. However, we are not able to obtain it using the inverse cosine because the domain doesn't allow that. But we can easily get it by doing this expression, by doing this. x4 is going to be... So how could you achieve this? Well, if you look carefully enough, you will see that it is 2 pi, right, minus x1. Because 2 pi would complete the whole revolution, but we are missing this much radians, and that much is x1. So we're going to just subtract x1, which is this value. Notice I'm not using the approximate because I don't need to. Let's keep it as exact as possible. And if we are asked to give an approximate result in the problem, we can provide it to the specified number of sig figs. And this is approximately equal to, I again calculated this beforehand. This gives you 5.79. And for x3, we are going to do something similar. The symmetry argument still holds, but this time for x2, we're going to do that. So if we were to reflect this x2 with respect to the x-axis, we see that there is another angle like this, which I will call x3. And to be able to get that x3, we in fact do the same thing that we just did. We're going to have 2 pi, and then we're going to subtract x2 from it, which is arc cosine of 1 minus the square root of 61 over 10. And that is approximately equal to, it is equal to 3.96. Okay? Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. And if you want to see further videos like this, please make sure to subscribe. And this is it for this video. I hope to see you in another video. Until then, take care.